a presentation and the next moves forward in astronomical history, looking at Tycho and Kepler. I'm having to retrain myself to pronounce Tycho's name as Tycho. For years I had called it Tycho or Tycho, which is actually the correct Danish pronunciation, but everyone in the English-speaking world seems to say Tycho, so I'll say that. Tycho Brahe is about the English pronunciation of his name. Something you might notice here is that this portrait is not nearly as good as the portrait on the left here. At least the portrait on the left is just a black and white drawing, but the one on the right is one that Tycho had done. He firmly believed that his right eye had grown larger from all his years of observing. And this was an interesting thing. Tycho lived 1546 to 1601, not a terribly long life. He accumulated large amounts of accurate observational data, and this is his key contribution to astronomy. Before Tycho, people would do observations, but they were all naked eye observations. They didn't use particularly good instruments, and they just weren't that accurate. For more than 20 years, he gathered data on not only stars, but also on the planets among those stars. And so he had accurate positions for those. For the brighter stars, he was able to determine their position to within 1 minute of arc or 1 minute of angle. And I'll show you in a minute here just what that might mean. He would also be able to do this for the planets as well. And this was a key, and the most important thing that he did was getting this accurate data. We should be able to see what this looks like. On this piece of paper here, I've drawn a right angle. You can see that's a 90-degree angle is what a right angle happens to be. And then I can draw a 1-degree angle on here. And for the 1-degree angle, I measured up a height over here that will produce that. Don't know how far I went. I went far enough. Anyway, here is a 1-degree angle, at least for as precisely as I could measure this. I had to go up, I think, 3.4 millimeters, and that's really hard to do. If I'd had a much longer line, I could have done a more precise measurement of it. But that's about a 1-degree angle. 1 minute of arc is 1/60th of a degree. So imagine that you could split this degree here, this 1-degree angle, into 60 parts, and a minute of arc would be 1/60th of that. That was how precisely Tycho measured the positions of the stars. And so that is absolutely amazing that he could do that. He thought the Copernican model was incorrect, but it was his observations that eventually helped support it. This is a kind of a fanciful drawing of one of his instruments. It's called a quadrant. Okay, who knows what this person is doing here? This isn't really needed. But the main part of the quadrant was this huge curve that he happened to have here, that you can see degree markings down here along the bottom. And then the observer, who would have been Tycho, is up here sighting along this quadrant, and he's got an instrument in front of his face so he can measure fractions of degrees, and he'd be viewing the star or planet through this little tiny window that's up here at the upper left. And then he's got assistants, one of whom reads the time here and on a clock, and then another one who writes down the observations. So it wasn't just the work of one man. He had servants who were taking care of some of the other things, but it was this huge radius on the quadrant. A quadrant is a fourth of a circle, and that's what allowed him to get that precision. I should stress here that Tycho's observations were pushing the limit of what was possible with the naked eye, and his were the best observations by far that anyone had ever made. They were also pre-telescope, all naked eye observations. Among the things that he did to improve his measurements, he found out that when he was trying to take the measurements from the upper levels of his castle or home or whatever it happened to be, it would have been built out of stone probably, but when there were strong winds, the measurements would be messed up by the motion of the house. And so he dug down on the island that he lived on and had his measuring instruments firmly attached to the bedrock of the island. And so that was something that he did. So he went to extreme lengths, especially for the late 1500s, to get accurate measurements. That brings us to the next person in this story, Johannes Kepler. Kepler was hired by Tycho to be his mathematical assistant in the last 18 months of Tycho's life. Tycho didn't know this was going to be the last 18 months of his life. His death came on rather suddenly. Kepler lived 1571 to 1630. These were difficult times in Northern Europe. He was the child of a mercenary soldier father and an innkeeper's daughter. He contributed 3 laws of planetary motion, the first proof of how logarithms worked. If you have ever used logarithms in a mathematics class, Kepler was probably the first person who ever put them to practical use, and he did it in analyzing Tycho's data. So that's why he happened to do that. And he produced a book of accurate planetary position tables. People had done these before, but they'd always been pretty much inaccurate, and they eventually became useless. But Kepler's did not, because he based his on accurate observations, those of Tycho. Kepler wasn't an observer himself. He actually had rather poor eyesight, so he could never have done the observations that Tycho did. On to Kepler's laws. First, the orbits of the planets are ellipses, with the sun at one focus. What in the world are ellipses and things like this? You probably all know how to draw a circle. You can do it with a pin stuck into a piece of paper and a loop of string. And if I just hang on to here, okay. Whoops, gonna go off the paper there, rats. But that would give me a pretty good circle there if I was to do something like that. I was having some slipping on the pin and the string, but that's a way you can do a circle. Now, to draw an ellipse, what we need are 2 pins instead. And when I draw an ellipse, I'll try to get the string stuck on my pin here just right. And that's an ellipse. Now, that ellipse probably looks a lot like a circle, but that's how you happen to get an ellipse. These 2 points are called the focuses, or the foci. I think that's the correct Latin way of saying it. But those are the focuses of the ellipse. And if I get them even farther apart for this particular loop of string, you can see something that is definitely not a circle, or definitely not a circle. Okay, now that's much more obviously an ellipse, but for the planetary orbits, actually, the distances that these pins would be apart for drawing a planetary orbit with this loop would actually be much less than the distance I've got now. And if I drew it, you'd have a hard time telling the difference between one of the planetary orbit ellipses and this circle that I drew as my first one. So we found out that the orbits of the planetary ellipses. Now, think about how hard this would have been to determine. Kepler was working with data that was taken from a moving planet that itself is on an elliptical orbit, and he's looking at moving objects that are on elliptical orbits. There was one point where he was trying to figure out the orbital shape of Mars, and he had come up with a circular orbit for Mars that disagreed with Tycho's data by 8 minutes of arc. Remember how small that 1 degree angle was? This would be about, roughly 1/8 of that very small angle was how much Kepler's circular orbit for Mars disagreed with Tycho's data, but Kepler knew that Tycho's data was better, and so he had to improve on that, and eventually he realized that the orbits of the planets are ellipses. It took him hundreds of pages of calculations, something on the order of 900 pages of calculations, and years of work to figure out that the planetary orbits were ellipses. The second law is that a line drawn from the sun to a planet will sweep out equal areas in equal time intervals. This one, I'll call up a computer simulation to show you what this looks like. Here's a demonstration of Kepler's second law, a simulation of it. And Kepler's second law says that a line drawn from the sun to a planet sweeps out equal areas in equal time intervals. And so this is for the planet Mercury, which has, of the planets that were known at the time of Kepler, it had the most elliptical orbit. And it's got some numbers up here that indicate that. We're not going to go into the mathematics of ellipses all that much, just that they happen to be that. But here's what happens. When a planet is far from the sun, the line from the sun to that planet is longest, but the planet moves slowest. And when it's nearest the sun, the line from the sun to a planet is shorter, but that's when it moves fastest. Let's see if we can have another object in here. Halley's Comet. Okay. Now, this has an extremely elliptical orbit. Notice how slow it's going way out there on the left and how it speeds up so much when it comes into the sun. Okay. Kepler figured out that that line from the sun to the planet will somehow sweep out equal areas in equal time intervals. And it's because the closer the planet is to the sun, the faster it orbits. And it does it in just such a way that that equal areas in equal time laws happens to be true. In modern language, we would say that what's going on is that something called angular momentum is conserved, and that the angular momentum of the planet remains constant. But at the time of Kepler, that language didn't exist. And so the equal areas in equal time thing is actually easier to understand than an abstract idea like angular momentum. Okay, if we look at Earth's orbit on here, Earth has the most nearly circular orbit of any of the planets, and it's hard to see what such a big deal about Kepler's third law happened to be. We could look at Mars' orbit, which is more elliptical than Earth's, and you can see a distinct difference between the distances on in the green there and the distances for the purple or magenta or whatever that color is. But anyway, it's most obvious for something like Halley's Comet. So that is Kepler's second law of planetary motion. Then we get to Kepler's third law. The third law is that there's a mathematical relation between the orbital period and the semi-major axis, so that P would be the orbital period, A is the semi-major axis, which I haven't defined yet, and C is the constant that is the same for everything in the solar system. Okay, this is a Word document that I've got on using Kepler's third law, and the third law stated verbally is the square of a planet's period, the orbital period, is proportional to the cube of its semi-major axis. And this is the way that I wrote it there. Now, none of the planets have orbits as elliptical as what I've drawn here, but it's easiest to illustrate it with something that's this extreme. And the idea is, if you have a circle, there's one number that describes the circle, and that is the radius of the circle. And it's constant, always the same. But with an ellipse, there are two numbers that define it. One is the long axis of the ellipse, and that's called the major axis. The other is the short axis of the ellipse. That's called the minor axis. We're concerned with the major axis, and that's I've got written as 2a here because half of that major axis is what's called the semi-major axis, half of that length. And semi, like a semicircle, is half of a circle. The semi-major axis is half of the major axis length. And so we're calling that 2a in this picture here. Now, let's do some actual work using this third law. In this Word document that I've got available for you to print off, you can do some work to get practice with Kepler's third law, but I'm going to show you how you do it first, so it'll work. And on the second page of it, I have a bunch of data for solar system objects where I give you the orbital period and have you figure out the semi-major axis. This is for practice, so you can master this because there will be a test question on this, so you'll get to demonstrate your mastery of it there. But I've got a bunch of things that you've heard of, no doubt. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto, and then Comet Halley and a bunch of other things. Now, every one of these things, if you look in the back of your textbook, or they may not all be in your textbook, but certainly the planets will be. And if you look on Wikipedia, if you look up Comet Halley on Wikipedia, you can find out what its semi-major axis happens to be. It'll probably give it to you both in kilometers maybe, or meters, and in astronomical units. But the point of this exercise is to learn how to use Kepler's third law. So I'll show you the mathematics of that here. All right, now we're looking at this again. And first of all, in Kepler's third law, P squared equals CA cubed. In this class, at least so far, when we learn this, we're going to be measuring the orbital period in years. And so P equals that's key. And then A is the semi-major axis. In something called astronomical units. And the abbreviation for an astronomical unit is an AU. The abbreviation for a year is just the letter Y. Now, an astronomical unit happens to be the semi-major axis of Earth's orbit. And so we just use Earth as a scale. The astronomical unit was used at the time of Kepler and was a common enough thing. They didn't actually know how far the astronomical unit was, just that that was the size of Earth's orbit. And they could figure out the size of the other planets' orbits based on observation, and they just used Earth's orbit as the the definition of the standard for that. The astronomical unit is still used by astronomers when they're looking at extrasolar planets. These are the planets orbiting stars other than our sun. They'll give the orbital radii, or the semi-major axes of the orbits, in astronomical units. It's just a convenient thing to be measuring stuff in. Now, the constant c is the same for every planet in the solar system, but so far we don't know it. But here's how you can figure it out. There is a planet where we happen to know what its orbital period is in years, and we know what its semi-major axis is, and that's the Earth. So for Earth, we can say that its orbital period, 1 year, if we square that, is equal to c, whatever that happens to be, times its semi-major axis, which is 1 astronomical unit, and that gets cubed. Okay, now, when you've got something in parentheses and you raise it to a power, something that's multiplied together, like 1 times year, you'll raise the number to the power and you'll raise the letter to the power as well. When you have units for physical quantities, they get treated just like algebraic quantities in an algebra equation. So the left side, 1 squared is still 1. The left side becomes 1 year squared. The right side is going to be c times, when I cube this, it'll be 1 AU cubed. Okay. And it's the AU is, as a whole, is cubed. That's what you do when you have 2-letter abbreviations. Well, if you solve for c, you find out that you get 1 year squared per AU cubed. That's what it happens to be. And it's just a conversion factor that takes you from years to astronomical units, or vice versa, depending on what you're doing. And so we'll remember that. Now, let's take on a few of these calculations here and see what they happen to be. I'll let you look up what some of these different things are on here, but I'll just do a calculation for a couple of them. (3525) Paul, okay, happens to be an asteroid. We're given that its semi-major axis is 3.081 astronomical units. So it's about 3 times as far from the sun as Earth happens to be. So 3525 Paul. And in the same region of space as this particular object, which is a solar system object, is 3 more solar system objects which have names of John, George, and Ringo. Okay, so John, Paul, George, and Ringo. Those were the names of the Beatles, the first names of the Beatles. These happen to be asteroids. They're between Mars and Jupiter, and often the discoverer of asteroids gets to name them, so somebody had some fun with this. But in this case, we know the semi-major axis. A is equal to 3.081 AU. Well, how long does it take to orbit? We can figure this out. P squared is CA cubed. And so I'm going to write this in here. C, remember, is 1 year squared per AU cubed. And then little a for this thing, the semi-major axis, 3.081 AU, and I cube that. Now, I'm going to cube that number first. So before I do anything else, I'll still have 1 year squared per AU cubed. And when I cube these parentheses here, to do that on my calculator, I go 3.081, and then I've got a button that looks like X to a box, and it gives me an exponent up here. I should dig out my, I don't know where I've got my TI-83 right now, but I'll show you how you do it on there in a second here. But I want to cube that number. So that's all I have to do. And I get 29.25. So 29.25, and that would be AU cubed. Okay. Now, these AU cubes will divide with those AU cubes, and I'll end up with P squared is equal to the units I have left on the right side are just years squared. So 29.25 years squared. That is not the orbital period. That's the square of the orbital period. So I have to take the square root of that number. And to do that on my calculator, I've got various ways. One way is to use my square root thing, and into that, if I go second and then the thing that's above the little minus sign on here says answer, it'll take that previous result and stick it in there. And you can probably do that on a TI-30 as well. And I just hit enter, and I get 5.408. Because I took the square root of that, that's what the square root of 29.25 is. The square root of y squared is just y. So this asteroid takes 5.408 years to orbit the sun. Now, when you actually do these things, sometimes the numbers you get will vary a little bit from what you'll find if you look it up on Wikipedia or something like that. But they shouldn't vary very much. The reason that they can vary is that the planets are also acted on by, or the objects orbiting the sun are also acted on by other planets. And in the case of an asteroid, it's also acted on by Jupiter, which can tweak the numbers a little bit, but still it should come out pretty close. Let's do one where we know the period and we're trying to find out the semi-major axis. And one, this C/1996 B2. I'll start a new piece of paper here, which is a pretty weird name, but here's what it happens to be. The C tells us it's a comet. Okay, so that's just how they designate those things. 1996 is its year of discovery. The B means that it was discovered in the second half of January. And so this relates to the time of discovery. If it was discovered in the first half of January, it would have been an A. If it was discovered in the first half of February, it would have been a C, and so forth. So January is AB, February is CD, March is EF, and so forth. And the 2 means that it was the second comet discovered in the second half of January. This one has the popular name, let's see, I think that's how you spell it. Not positive about that, but I'm pretty sure. It was discovered by a Japanese amateur astronomer whose last name was Hyakutake. And he discovered it with binoculars. Not just any old binoculars. These were binoculars that have a 6-inch objective lens. And so the diameter of the objective lens, each of the barrels on these binoculars was a circle this big. And so they were pretty good binoculars. I would love to have a pair of those. They were made by a company called Fujinon, and I've had the pleasure of looking through them a few times. They weren't my own, they were at a star party, but they're incredible. I see better through binoculars than I do through a telescope. I just like the view better. But anyway, this thing happens to have a 14,000 year orbit. This came by in 1996. It was discovered in January. It passed within just a few million miles of the Earth. I can't remember how many it was, but we hadn't even known about it. It's kind of scary to realize that it had its closest approach at about the end of March. So about 2.5 months after its discovery is when it had its closest approach to Earth. It sort of makes the disaster movies about comets and things hitting the Earth a little more believable, where we didn't even know about this thing. And then within 2.5 months of its discovery, it had its closest approach. I thought this would be the best comet I would ever see in my life. You could see its tail from the Walmart parking lot in Moses Lake. It was just incredible. But orbital period of 14,000 years. How in the world did they figure that out? Well, I'll talk about that in a minute. Let's figure out its semi-major axis first. So p squared equals CA cubed. It's A that we want, so I'm going to divide p squared by c. And so A cubed will equal p squared divided by c, and p is those 14,000 years. This was just an early estimate of its orbital period, but it's one I like to use. Square that. On the bottom, I will have 1 year squared per AU cubed. Now, when you square 14,000 years, you're going to get something in years squared, which is a big number. 140, whoops, turn on calculator first, 14000 x squared. And I get 1.96 times 10 to the 8th, and that's using scientific notation, but it's handier here. And that's years squared. Now on the bottom, I've got 1 year squared per AU cubed. Okay, when you divide by a fraction, you invert and multiply. And this is what I do to figure out the units on things. On top, I've got years squared. On the bottom, I've got years squared per AU cubed. When you divide by a fraction, you flip it and multiply. So the units become years squared times, whoops, that's an AU cubed, times AU cubed over years squared. And the years squared divide out, and I just get AU cubed. And so what the result of that is that A cubed is equal to 1.96 times 10 to the 8th AU cubed. Now, that's not the semi-major axis. That's the cube of the semi-major axis. So I have to raise it to the 1/3 on my calculator. Now, this calculator, it happens to be really easy to do that on. Other calculators may not be so simple. I've got YouTube videos that you can watch with other less sophisticated TI calculators. They've got a caret button on them, and you can watch that if you want to know how to do that. But on this calculator, I just take that number that I've got there and hit my little X to the box button. And in the box, I want to have 1/3, which is what happens when you take a cube root of something. So A will equal this. It's 1.96 times 10 to the 8th AU cubed to the 1/3. Okay, or you could think of it as a cube root. The same thing, 1.96 times 10 to the 8th AU cubed. But at any rate, I'll stick a 1/3 up there, just 1 divided by 3, and I get the semi-major axis of Hyakutake's orbit is about 580 astronomical units. Okay, which means it's roughly 580 times as far from the sun on average as the Earth happens to be. It does come in close sometimes, but that's how you do that. Okay, as I mentioned, I've got other videos on YouTube of me doing similar calculations with this, but you can practice with all of these things. And oh, how did astronomers figure this out? That thing had a 14,000 year orbit? Well, they figured out the shape of its orbit first. If this is the sun sitting in here, and Hyakutake visited the sun with this close approach. Okay. Now, if it traveled along a straight line, all you'd have to do is just get 2 points, and 2 points determine a straight line. But to get the orbit of an ellipse, you need 3 points. However, if those 3 points are too close together, you don't get a very accurate determination. And this is a reason that when astronomers, when you first hear about a new comet being discovered, you'll hear things like astronomers estimate its orbital period to be some amount. And it's just an estimate at first. And the difficulty is, if these points are too close together, it's hard to determine the whole orbit or the whole equation for the eclipse, especially because it's hard to tell where the center of the comet is, because they've got this tail of stuff that's coming off of them. And so it's better if they wait a while, get some more observations, and then they can produce a pretty accurate orbital equation. And so from these observations, they can determine the equation of the ellipse. And built into the equation of the ellipse is the semi-major axis. And so you get that. And then once you know the semi-major axis, you can calculate the orbital period. So they go in the reverse order. I gave you the orbital period and we figured out the semi-major axis. But I want you to be able to go both directions, which is why I'd like you to practice with as many of these as you can. Then look up the answers on Wikipedia or in the back of your book. You could restrict yourself to the planets if you want to. I've got a mix of them. Those are things. However, if you look up what some of these things are on Wikipedia, you can learn some interesting things about astronomy.